All right, today we're talking about geometric sequences and series. So just to review the previous lesson on arithmetic sequences, remember that those are modeled by linear functions. Like when we simplify them, they kind of look like an equation of a line. This is very similar to y equals mx plus b form. Okay. Geometric sequences are modeled by exponential functions. So we'll see them like we had seen previously in our chapter on exponential functions, where our variable, or in this case the position number, is an exponent. And what makes something geometric is that all terms will have a common ratio. So geometric sequences will look like we're multiplying or dividing by a number. So for instance, if I had the list 32, 16, 8, 4, 2, 1, etc. Okay, here it appears our pattern is that we are dividing by 2 each time, right? Divide by 2, divide by 2. My number's getting cut in half. Now, r, though, is always in terms of multiplication. What are they multiplying by to get to the next term? That could even be a fraction. But here, we can calculate this common ratio by dividing any term by the previous term. So obviously don't use the first one because there's no previous term. But take any term, divide it by the previous one. So if you do that, 8 divided by 16 reduces to 1/2. They are multiplying by 1/2, right? Which is cutting our value in half every time we go to the right. So we'd say r is 1/2. Okay, so r is equal to any term divided by the previous term. This is also a way to guarantee a list is geometric. If you were to do this again, right, take any term and divide it by the previous term, pick some easy numbers this time, and they reduce to the same ratio, then we can say all terms have a common ratio, and that makes it geometric. Okay, here is a formula that we can use to find any term in a geometric series, sequence that is n terms away. So n here is kind of our position number, right? Like 32 would have been the first term, 16 is the second, 8 is the third, fourth, fifth, etc. So if I wanted to find the 100th term, which will obviously be some sort of fraction, if we keep dividing by 2 or multiplying by 1/2, we can use this nice formula. Okay, so in this formula, we have the nth term equals the first term times our common ratio to the n minus 1 power. Okay, and again, there's this adjustment because there's no 0th term. So typically we will usually see an n minus 1 in our formula. Okay, let's try a few examples with this. So here is a list, 10, 20, 40, 80, 160, and it appears my numbers are doubling. Now, if you note what they're just multiplying by, in this case 2, then that's directly r. We can just say r is positive 2. Now you could confirm this by taking any term and divide it by the previous term. And of course 20 divided by 10 reduces to 2 over 1 or 2, right? They're multiplying by 2. So if it was less obvious, we can always use that method as well. But we now know r is positive 2. It says find the next two terms of the geometric sequence. Well, if we doubled that, we'd get 320. And if we doubled that, we'd get 640. Those would be our next two terms. Now find the 10th term. Well, I could just keep doubling, right? We've got 1, 2, 3, 4, 5, 6, 7 terms already. We just need to do this 3 more times. But let's go ahead and use our fancy formula. The value of the 10th term, so the 10th term equals our first term, which they gave us here is 10, times our common ratio, which we figured out was 2, raised to the n minus 1 power. Well, in this case, n is 10, so to the 10 minus 1 power. Okay, so again, because Desmos sometimes is a little finicky about keeping you up in your exponent, you would either have to type in 10 minus 1 in parentheses, or of course, you can just simplify that to the 9th power. So if we double 9 times and start with 10, that 10th term out there is 5,120. Okay, our next one says write the explicit formula. That's this formula. We're just going to keep n as n when we write our formula, and then use it to find the 8th term. Okay, so if we're writing the explicit formula, we'd say the value of the nth term equals, we need the first term, which is 4, and the common ratio. Now here, it does appear our numbers are getting larger, so I think we're multiplying, but notice that they're alternating signs, right? Negative, positive, negative, positive. Well, again, we can always figure out r by taking any term, so I'm going to take negative 12, and divide it by the previous term over 4 to figure out what they're multiplying by here. And in this case, they're multiplying by negative 3, and you definitely need parentheses here when you go to plug this in the calculator. But for the explicit formula, we just leave n as n. So this is the explicit formula. Now we need to find the 8th term. So we just go back and plug in 8 into the formula. So the value of the 8th term is 4 times negative 3 to the 8 minus 1 power, or 7th power. Okay, again, make sure you have your r in parentheses here, especially when it's a negative value. If you multiply by negative 3 7 times and start with 4, we end up getting negative 8,748. Okay, so there is our 8th term. Okay, write the explicit formula. Given the 4th term is 128 and the common ratio is 2. Now note, to use this formula, I need the first term and common ratio. I know the common ratio, but they have not given me the first term. So how can I use this to find it? Well, I could think about our position number, right? The position number they gave us is the 4th value. So I could say, well, I don't know 1, 2, or 3, but I know the 4th term out is 128. And I know if I wanted to continue this pattern, we would be multiplying by 2 as I went to the right. So if we doubled that, we'd get 256 would be the 5th term. Well, I could also use that to go backwards, so we're not too far from the first term. If I, instead of multiplying by 2, we divided by 2 or multiplied by its reciprocal, right? 2 over 1 is reciprocal. We could go backwards. So kind of cutting in half, we'd get 64, 32, and 16. So I could kind of reason my way back to the first term there. We can also algebraically find it. If I know that at position 4, our value is 128, I can plug in the value here of 128 and a position of 4 for n. Now, I don't know the first term, so we could algebraically solve for it, but my common ratio is 2, and we get 128 at position 4, so 4 minus 1. So we can algebraically solve for the first term here. 4 minus 1 is 3. 2 cubed becomes 8. So the first term times 8 equals 128, and if you divide by 8, we end up getting 16 is the first term. So we can algebraically solve for it, or because we were pretty close here, we could probably just reason our way back. But now we have the first term, we've got our common ratio, we can write our formula. The value of the nth term equals the first term, 16, times our common ratio, which was 2, to the n minus 1 power. There's our formula. Now let's find the 10th term. Okay, so we just plug in 10 for n, right? 10 minus 1 power. Let's go to our calculator. So I went ahead and simplified to the 9th power here, but if you multiplied by 2 9 times, starting with 16, we end up with 8,192 is our 10th term. Okay, so what if they just gave you a sequence and they want to know, is this sequence geometric, arithmetic? So remember, arithmetic should look like they're adding or subtracting something over and over again. Geometric, to the naked eye, will look like they're multiplying or dividing. Now we know r is always written in terms of multiplication, but that's kind of a way of telling if something is geometric, or does it follow some other pattern that's neither? So let's go ahead and check. Here, it looks like my values are going down. So I'm thinking maybe in terms of subtraction, that's down 2, that's down 2, that's down 2. They're subtracting over and over again. This is arithmetic. Now it says if it is arithmetic or geometric, find the common difference d or the common ratio r. Here the common difference, what they're subtracting over and over again, is -2. For our next one, I see my numbers are alternating again, which makes me think they're multiplying by a negative number. So I'm thinking in terms of geometric, but how do I tell if it's really geometric? Well, let's see if we can calculate r. If I take any term and divide it by the previous term. Now again, think about when you're dividing by a fraction, that's the same as multiplying by its reciprocal, which would give me negative 2 over 4. Remember, top times top, bottom times bottom. And if you simplify that, we get negative 1/2. Okay, now to guarantee it's geometric, I need to show that there is a common ratio. Like if I did this again, that when I reduce, I should get negative 1/2 again. So let's try this one more time. What if I take positive 1/8 divided by the previous term, negative 1/4. We're going to multiply again by the reciprocal. So we flip the second one upside down, top times top, bottom times bottom, we get negative 4/8, which is negative 1/2. We do have a common ratio. We've guaranteed it's geometric, and we know the common ratio is negative 1/2. Okay, our next one, let's see, maybe they're multiplying by 3. Nope, because 3 times 3 would be 9, not 6. So maybe they're adding. My numbers are getting bigger, so at plus 2, plus 3, plus 4, plus 5. There's definitely a pattern here, but because it's not the same value they're adding over and over again, it is not arithmetic. And I could already tell if you tried a common ratio, my ratio here would be 3 over 1 or 3. 6 over 3 would be 2. Those don't match. It's not geometric. This is definitely a neither or neither. There's definitely a pattern there, but it's not considered arithmetic or geometric. Okay, what about geometric series? What if I want to add up a bunch of numbers that kind of follow a geometric pattern? A geometric series is the sum, meaning to add up, a finite number, meaning, 10 terms, 20 terms, we're not going to infinity. So some finite number of terms of a geometric sequence if we want to add them up. And this is our formula we can use to add up the first n terms. Now it's a little different than the arithmetic one. In this case, we need the first term, like we did before, but I don't need to know the last term. Instead, all we need to know is the common ratio, which goes in 2 places here, and the number of terms, how many terms we're adding up. So that's it. First term, common ratio, and the number of terms. So let's try a few examples here. Find the sum of the first 12 terms. Okay, well I know n is 12. So that's one of the 3 things we need. Here's my first term. So I can say the first term is 7. And the only other thing I need is the common ratio. And they've given me enough terms we can figure it out. It looks like they're multiplying by 2 to go from one term to the next. And because it's in terms of multiplication, yeah, r is 2. So we've got all of our information here. So let's follow the formula. The sum of the first 12 terms equals the first term, 7, times kind of big parentheses and a fraction here, of r to the n power. So always put r in parentheses, to the 12th power, it's a good thing we're using a calculator, minus 1 over r minus 1. So 2 minus 1. Now, the bottom doesn't necessarily need to be in parentheses because we're just subtracting, but up here where you have an exponent, you definitely want your parentheses. So let's go to Desmos. And in fact, let's let it do all of the operations for us. We'll make less mistakes that way. So here I'll show you how to type this in since it's a little more complicated. We're going to type in 7 times parentheses and just hit divide to start a fraction right away. So parentheses 2 to the 12th power minus 1 outside of our parentheses to the 2 minus 1 power. Okay, now full disclosure, this formula is slightly different than the standard formula. I'll show you the difference in a second here. But the correct answer is 28,665. 28,665. It's the sum of the first 12 terms. Now I said that this formula that I'm giving you guys is slightly different than the standard formula. Okay, the standard formula really looks like this. The sum of the first n terms equals the first term times 1 minus r to the n over 1 minus r. So the only difference between ours and theirs is r to the n minus 1 and r minus 1, or the 1 minus r. It's essentially like multiplying this fraction top and bottom by -1. I just think this makes so much more sense. Why would you want to do 1 minus a number and calculate a negative down here a large majority of the time and get a big negative number? And what's a negative divided by a negative? It's positive anyway. So I don't know why they just didn't simplify it to that form. So if you do see this other formula, it will give you the exact same answer. I'll show you in Desmos right now. So if we swap these and instead did 1 minus that value and 1 minus 2, it's the exact same answer. If you see the other version of the formula, just know it's exactly the same. It's just like multiplying the fraction top and bottom by -1. Okay, let's take a look at this. Find the sum of the first 15 terms. Okay, well, n is 15. That's my number of terms. We've got one of our three things we need. There's my first term again. The first term is -512. And I just need the common ratio. Maybe it's a little tougher this time. Now these minus signs, just think of that as plus a negative number. So don't let that confuse you. But I think we're alternating between positive and negatives. Let's go ahead and find r using our common ratio. So r can be any number. I'm just choosing the smallest numbers I can here over the previous term, -128. And in fact, if you reduce this all the way down, those are both divisible by 64. You get -1/2. R is -1/2. Okay, we've got all of our information. Let's find the sum of the first 15 terms. So we plug in our first term, -512 times. And again, I'm just using our version here. It doesn't matter which one you want to use. R in parentheses, very important this time, especially when it's negative, to the nth power -1 over r minus 1. Again, the r in the bottom, if it's not being raised to a power, it doesn't necessarily have to be in parentheses. But let's go ahead and type this one in as well. Okay, so here we are. Got everything plugged in. And we get, well, a pretty ugly value. I mean, eventually, I guess we probably get into fractions. So it's giving me this very ugly decimal. And Desmos does give me an option to turn that into its fraction counterpart, which I like a little nicer. So this ends up being, now you could say approximately -341.3, or we'll go ahead and use this exact answer, -10,923 over 32. So if you're to generate 15 terms, so 11 more terms, and add up all those positive and negative numbers, you end up with that fraction. Okay, last couple here. Here's our formula again for reference. Find the number of terms. This time our unknown is an exponent. Well, what would we need to use eventually to solve for an unknown exponent? Logarithms, that's right, logarithms. I can't write an H. Logarithms, we're gonna need logarithms here. So let's figure out how to do this mess. So let's plug in what we know. I don't know how many terms. Let's see, if I was given this series that would give this sum. Well, we actually have a value to plug in for the sum. So let's go ahead and plug that in on the left. 1,048,575 equals our first term, that I do know, it's 1, times our fraction here. R, our common ratio, looks like we're doubling, so times 2, which means R is 2. So we can plug that in, 2 to the n power -1 over 2 minus 1. Now let's go ahead and simplify in the bottom here. I can do 2 minus 1, of course, is 1. I don't really need the parentheses necessarily on 2 here since it's a nice positive value. And the bottom simplifies to 1. So a couple things we would normally do. It would actually probably be best to divide away the first term. It just happens to be a 1. But that's a nice easy way to get that 1 away from our fraction. It's held with multiplication. Of course, dividing by 1 is not going to change the equation much, but that's what I would normally do with that first term. So we'll include that step. 575 equals. Now I don't have that 1 in front. I don't even need parentheses anymore with this fraction. So how about I get rid of the 1 in the denominator? Well, let's multiply both sides by that denominator, which is 1. Not a lot of things are changing here, dividing by 1 and then eventually multiplying by 1. But that's okay, we're getting somewhere. 48575. We just haven't need to go to a calculator yet. Equals 2 to the n minus 1. And I apologize, this should be a power. Didn't write that up there nicely enough. Okay, well, we're getting close. How would I get rid of this? Well, let's add 1 over. All right, it's minus 1. Let's add 1 over. And now I know 2 to the n equals 1,048,576. And here's where we can go to logarithms. We're going to use the base of our unknown exponent. Remember, our goal was to really get this by itself the whole time, right? So we got rid of the multiplier in front. We eventually got rid of the fraction and added away the 1. So now we can take log base 2 of both sides. 576 equals log base 2 of 2 to the n power. Here, log base 2 of 2 cancels, and I get n equals this logarithm. So let's go to Desmos. Okay, so we need to use change of base. Remember with Desmos, and the base goes in the bottom, drop the base, or the base goes in the basement. So here is our logarithm with change of base, and it tells me the number of terms we would need to add to get that total is 20. We would need to add 20 terms. Now note, when we're talking about n, the number of terms, it has to be a positive number, and it has to be a whole number. I can't add 3 1/4 terms, right? There has to be a finite whole number of terms. Now, if I can't get to that exact number with a nice positive whole number like this, then either the problem's designed wrong or I did something wrong. Okay, in our next one here, it's very similar. I would say maybe try this one out. Your common ratio here is actually -3. They're multiplying by -3 to get this alternating series. Your first term is -2, and here is your summation, and you need to solve for n. So this would be a good one to pause and try out, and after you unpause, I'll have the answer up. All right, well, this one's definitely a little trickier than the previous problem, and I remember why I included this in the notes. So here you would want to get rid of your first term, right? To get rid of that multiplier. Again, our goal is to kind of get this base here by itself with our unknown exponent. So we can just divide away the -2 that's held with multiplication. Then we don't even need these outer parentheses. We can get rid of the denominator, which simplifies to -4 by multiplying that answer by -4. We can add our 1 over. And here's where we might get an issue. If you try to use a negative base, logarithms are not defined. So what you have to do is basically just use the positive base. So use base 3. I know this is we're kind of cheating a little bit here, but you can't use negative bases for logarithms. So if you do have a negative r value, which is a weird case, but it does come up, you just basically treat it like a positive number, like 3 to the n. Okay, and to get to this value, this also has to be a positive number, or we're going to be in trouble. Logarithms won't be defined there. But we do get n is 12, and that seems like a reasonable value. You could generate more terms and check, but that is what gives you this sum. So if you do get a negative base, you have to make it positive. If they give you a negative number in here, you kind of have to just kind of treat it positive so that we can use logarithms. So a little tricky at the end, but the answer was 12. Okay, we'll definitely do more class or examples like this in class. Thank you guys.